Quantum levitation, as it is called, is a process where scientists use the properties of quantum physics to levitate an object, specifically a superconductor, over a magnetic source, specifically a quantum levitation track designed for this purpose. What's quantum physics, you might be wondering? Quantum physics is the branch of physics concerned with quantum theory. The quantum theory is the theoretical basis of modern physics that explains the nature and behavior of matter and energy on the atomic and subatomic level. So, essentially think of quantum levitation as scientists making things levitate and lock in the air. Now to superconductors. Scientists cannot just quantum levitate anything. It has to be specifically a superconductor. A superconductor is an object that conducts electrical current with basically zero resistance. There are type 1 and type 2 superconductors, but only type 2 can achieve quantum levitation. Type 1 superconductors go from normal to superconducting state instantly and cannot be penetrated by magnetic field lines, while type 2 become superconductors through a slow transition. They can also be penetrated by some magnetic field lines. In order for certain materials to reach the superconductor status, they have to be cooled to very low temperatures. This capacity produces interesting and potentially useful effects. For a material to behave as a superconductor, low temperatures are required. So, remember, for the purposes of quantum levitation, we don't necessarily care about type 1 superconductors because they are not able to quantum levitate or to flux pin. What we are specifically concerned for in the context of quantum levitation is a type 2 superconductor because of their unusual ability to allow small filaments of magnetic field to go through them. Now, let's talk about the Meissner effect. The Meissner effect is when a material transitions to the superconducting state and all magnetic fields are excluded from its interior. Type 2 superconductors are a different story. The magnetic fields in a type 2 superconductor is not completely excluded. Rather, it is constrained in filaments within the material. The filaments are surrounded by a supercurrent while in its normal state, leading to a vortex state. A vortex state for type 2 superconductors allows magnetic field penetration. This is what causes the quantum locking of the superconductor. Now, let's get into some flux pinning. According to the Meissner effect, the superconductor will tend to expel all magnetic fields inside of it. Type 2 superconductors have extremely thin magnetic fields penetrating them. This is called flux tubes. Inside each of the magnetic flux tubes, superconductivity is destroyed, causing the superconductor to keep the magnetic tubes pinned in the weak areas. In this state, if you move the superconductor, the flux tubes will move, causing the superconductor to be trapped in mid-air, which leads to the floating appearance. So, remember, quantum levitation is constrained by its needs for extremely cold temperatures. The act of actually being able to levitate things on the quantum level has some major implications in terms of future technology or things we could use to advance society, but the main holdback is definitely the need for that cold temperature. Hypothetically, if scientists are able to create or find a superconductor with an easily achievable critical temperature, it could mean so many things for our society. Such an advancement would entail scientists making pretty much anything levitate with ease on specialized tracks. We could pave roads with magnets and have flying cars, create skate parks meant for hoverboards, frictionless transportation, and so much more. One of the most interesting and innovative implications comes from Chinese architect Wai Zhao. Zhao proposes this technology could be used to create a quantum-locked city in place. This city can be slowly rotated in place, generating energy. This would mean floating cities that alleviate overcrowding problems and also create completely sustainable energy. Now, for a quick video demonstration about what quantum levitation actually entails in the real world. This specific video shows a superconductor floating about a Mobius strip, so enjoy.
Wow!